symmetry. So a figure has a line symmetry, or you can think of it as reflection symmetry, if it can be reflected across a line so that the image coincides with the pre-image. Okay, so what does coincide mean? Kind of. Yeah, it's like, so if they're, yeah, if the image coincides, it's going to be one right on top of the other. Okay, and it'll look the exact same. So the line of symmetry, which can be called the axis of symmetry, is going to divide your shape into two congruent halves. Okay, so a heart is going to have one line of symmetry because you could fold that heart over that line and it would overlap, okay, and it would perfectly coincide with it. For the first example, I don't want you to see that yet. For your first example, you have to tell whether each figure has line symmetry, and then if it does, then you're going to copy the shape and draw all the lines of symmetry. So when you're doing this for your homework, you will have to copy the shape. Obviously, you guys already have it on here, so you don't have to copy it. We can draw right on there. So remember, a line of symmetry is going to cut that object so that you would be able to fold it over and they would coincide. So one of your lines of symmetry, and usually they mark them with dashed lines, is what you'll see. So I could cut this star shape right in half, right? Wouldn't that be a line of symmetry? Okay, so vertically, how else could I cut this? Horizontally, so that would be 2. Can I cut this diagonally? Yeah. If you actually look at the shape, see how if I were to rotate it, it's the same no matter which way you do it? So you could actually do a line of symmetry through every point that it has. Do you guys know how many lines of symmetry a circle has? An infinite amount. Huh? Okay, so here we just drew 1, 2, 3, 4. Okay, so we have 4 lines of symmetry. Anywhere else? Uh-huh. Yes, yep. Good use of terminology. Okay, at the parts where it's concave, right? So at this point here, right, if I folded it in half here, it's going to match. So not only at every point that's exterior, but also the points that are interior. Doesn't this look like a beautiful star? Yeah, it does. It does look like a snowflake. Okay, so I had 4 before, and now I just added in 1, 2, 3, 4 more. Okay, so there are going to be 8 total lines. So this is yes, there are 8 lines of symmetry. Okay, and for a shape like this too, it might be fun and helpful to color code, so that way you don't count the same line twice, because there are a lot of lines of symmetry there. Okay, what about B? Is there anywhere I could do a line where it would cut that in half? No, if I do this, it's not going to work. If I do it straight down, at a diagonal, nope. So that's going to be no. Okay, and then we do have some line of symmetry for C. So where's one line of symmetry? Straight down. This is like a plus sign here. Could I cut it in half? Yep. And then could I cut it in a diagonal fashion? Yeah, I'd have to make sure that I line up these. And then I could also do the other diagonal. Okay, so remember you do have to put your lines of symmetry in there. Okay, any others? Nope. If you cut it from here to here, that's not going to line up exactly. Okay, so they're going to be yes, and there are 4 lines of symmetry. Right, and then if you're ever unsure, you could also cut out a shape, and then you could fold it. So if you can fold it and one goes over the other one, then you know that it's a line of symmetry. Alright, let's go to the next page. So the next type of symmetry we're going to talk about is called rotational symmetry. And rotational symmetry is when you have a figure that can be rotated about a point by an angle greater than 0 and less than 360. And then again, that image is going to coincide with the pre-image. Alright, so for example 2, we're going to identify rotational symmetry. If the figure has rotational symmetry, we are going to give the angle of rotational symmetry and the order. Okay, so with this shape, you would have to turn it and be able to rotate it about a point that has an angle greater than 0, okay, and less than 360. Okay, so is there any way that you can turn this so that it's going to look exactly the way that it does now? So like if you turned it 90 degrees, see how you'd have like these 3 lines here going this way, right? If you turned it 90 degrees and it would be like that, so it wouldn't look the same. If it was 180, instead of going like this, it would be boom, 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 and then the 2 lines. Okay, so this is going to be no. So you can't turn it so that it coincides with itself. Okay, and then what about this? Kind of looks like a flag. Okay, so yeah, what do you know what way? How many degrees? Yep, 180. So if you did 180 rotation, if you took that shape and you rotated it 180 degrees, it would be the same. Okay, and then it is asking you for the order. So the order is like how many turns you could get to be in the 360. So this is what you'd ask yourself. How many times does 180 go into 360? Twice. So then the order would be 2. Okay, so there are 2 times that you could do that rotation between 0 and 360. Okay, and then for C, this is also going to have rotational symmetry. What's the first time you could rotate it so that you'd have the exact same shape? Yeah, 90. And how many times does 90 go into 360? 4 times. Okay, so then that would be the order. Okay, so we did 3 things there. So you're telling whether each figure has rotational symmetry, so that's yes or no. And then if yes, rotational symmetry and the order. Okay, so you have to have the angle and then the order. So the order is how many times. How are you guys doing with that? You don't want me to cut it out and prove to you? I can just turn the page, right? Okay, so if it was 90 degrees, you could turn the page this way and it wouldn't look the same. If you can turn it upside down, does it look the same as it does here? Yep, so then that would be 180. This would be 270. And then obviously 360 would go back to the beginning. So yeah, if I just turn my paper 90 degrees, right, then it looks the exact same as it does here, doesn't it? Yeah, and then that happens every time you rotate 90 degrees. Okay, so it happens all of those times. So if I look at this, right, are those going to match? No. Are these going to match? Sorry, you can't see that. Nope. Are these going to match? Nope. Okay, so then so then there's going to be no rotational symmetry. Okay, now we're going to do the design application. So we're going to describe the symmetry of each icon. And then we're going to copy each shape and draw any lines of symmetry. So we don't have to copy the shape because we have it on here, but on your homework that's what you'll do. And then if there is rotational symmetry, then you're going to give the angle and the order. Okay, and let's actually just write a little note here that the order is how many rotations in 360 degrees. Okay, so if you do 360 divided by 2, you're going to get, divided by 180, you're going to get 2, and that's why 2 is the order for B. If you do 360 divided by 90, you'll get 4. That's why 4 is the order for C. Do you guys know what this is called? Yeah, yin-yang. Okay, so with this, is there going to be any line symmetry? No. Okay, so a circle does, but there's no way that you can cut this where it's going to overlap and it's going to look the exact same. Okay, because you have the black and the white portions. So there's no line symmetry. And then let's talk about rotational symmetry. So if it's rotational symmetry, remember, I would be able to turn this and it would look the exact same. That's a 90-degree turn. Does it look the exact same? Nope. 180? Nope. It's really close, but the colors are off. And then this would be the 270. So nope, there's no line symmetry, and there is no rotational symmetry. Okay, and I don't know what this icon is. Do you guys know?
A square.
Yeah, square and a square. Okay, so is there going to be line symmetry for this one? Yes. Okay, so yes, there are blank lines of symmetry. Let's figure out how many there are. So, I always start with, can I cut it down the middle? Yep. Can I cut it in half? Yep. Okay, can I cut it anywhere else? Diagonally. Yep, so that would fold over, and then this diagonal here. Anywhere else? Nope. Okay, so then I have 1, 2, 3, 4 lines of symmetry. Okay, and then let's talk about rotational symmetry. Okay, so remember rotational symmetry means I could turn it and it would look the same. When I turn this 90 degrees, does it look the same? Yep. Okay, so this is going to be yes. There is rotational symmetry. Let's say of 90 degrees. And that means the order would be what? Is 4. Okay, because 360 divided by 90 is going to be 4. Alright. Let's go to the next page. Okay, so now what we're going to do is apply symmetry to 3 dimensions. So we're going to tell whether each figure has plane symmetry, symmetry about an axis, or neither. Okay, so plane symmetry, symmetry about an axis, or neither. Okay, so before we can do this, we have to know what each one of these are. Okay, so we're going to write down our definitions. So the first one is for plane symmetry, and we're just going to put this at the bottom of the page here. Okay, so plane symmetry So a 3D figure has plane symmetry if a plane can divide the figure into two congruent reflected halves. Okay, so if a plane can divide the figure into two congruent reflected halves. So remember, a plane is just like a rectangle. Okay, I like to think of it as a piece of paper. So if you can cut the shape with a piece of paper and it would cut it directly in half, where one half reflected the other, it would have plane symmetry. Okay, and then the symmetry about the axis is the second type. Okay, and the symmetry about an axis is going to occur in a 3D figure. So a 3D figure has symmetry about an axis if there is a line about which the figure can be rotated. And that rotation degree, this has to be by a degree greater than 0 and less than 360. So just like before. Okay, so a 3D figure has symmetry about an axis if there's a line about which the figure can be rotated. That has to be by a degree greater than 0 and less than 360. So it can be rotated so that the image coincides with the pre-image. Okay, so now we're going to talk about our two shapes of it. Okay, so the first one is plane symmetry. So if it has plane symmetry, it means that you could take a piece of paper and chop that pyramid in half. Okay? Now, this pyramid, let's look at the base, right? Is the base a regular polygon? Yeah. Okay, so if it's a regular polygon, you're going to be able to cut it in half. Okay, so we're going to draw a picture of this. So really what you have to imagine is a piece of paper slicing this in half. And I drew my own pyramid, which leaves a little to be desired. Okay, so this was my pyramid that I drew. Then I said, okay, if I cut this in half with a piece of paper, right? This would be your plane symmetry. And this would be your front half of your shape. So I'm sorry, I know that's not very beautiful. Okay, so you would have this front half equal to the back half if you cut that. So there is going to be plane symmetry. Okay, so imagine like one of the pyramids in Egypt, right? If you were looking at it from one side, would it look the same if you looked at it from the other side? Yeah, right? Because you could cut it in half and they would be the same on both sides. Okay, and then let's talk about symmetry about an axis. So there should be a line about which the figure can be rotated so that the image coincides with the pre-image. So if you think of this line that happens through the center of the shape, would you be able to turn that a certain degree and have it look the same? So pretty much you want to imagine a pyramid just like on a pencil, right? If you were able to turn it and it would look the same, then you know it's going to have rotational symmetry. Okay, so, or symmetry about an axis. So the plane symmetry and the symmetry about the axis are going to occur for this one. Okay, and then you don't have to say what the degree is, but could you guys tell me what the degree is that you could rotate this? Yeah, you could rotate it 90 degrees. Okay, you could actually even rotate it 45 because it's a square. So like if you rotated a pyramid 90 degrees, it would still look the same. Okay, and then for B. Okay, so for B we have this block L shape. Is there a way that I could cut that with a piece of paper such that it would be the same on both sides? Yeah. Okay, yeah, you could just cut it right down the middle, right? You could cut it right here. Right? If you cut that with like a sheet of paper, then you'd have this first half here, which would be equal to the second half. Okay, so it does have plane symmetry. Here, this looked a little better, right? Where you cut it down the half. And then, so symmetry about an axis. So you want to think, okay, if I turn this on a line, would I be able to rotate it? Now, because of this specific shape where you have like the L, every time you rotate it, it would be a little bit different about that line. Okay, it would not be the exact same because you have that edge sticking out. So it's only going to be plane symmetry. Section we're going to do is 12.7, and 12.7 is all about dilations. Okay? And first let's define a dilation. We're just going to do that right up here. So a dilation. Have you guys heard of a dilation before? Okay, so it's a transformation that changes the size, but not the shape. Okay, so the shape is the same, it just gets larger or smaller. Okay, like if you have a picture and you want to enlarge it, okay, or if you have a big picture and you want to make it smaller, okay, that would be a dilation. So for example 1, we're just going to tell whether each transformation appears to be a dilation, and then explain. Okay, so is this going to be the same shape? No, okay, you're expanding this part here. So this is no, because they are not the same shape. Only part of the figure was enlarged. Okay, what about B? Yes. Okay, so yes. Yes, they are the same shape but different sizes. then we're going to talk about dilations in the coordinate plane. Okay, so some coordinate plane work like we did yesterday. So if you have a point that's the pre-image of a point under a dilation that's centered at the origin with a scale factor of k, then the image of the point is kx times ky. Okay, so what that means is you're going to multiply x by that scale factor k, and you're going to multiply y by the scale factor k. So remember yesterday we had those rules. Here's another rule. Okay, and then we're just going to write out what that means. So we are going to multiply x and y by the scale factor k. Okay, so we're going to multiply x and y by the scale factor k. Alright, ready for your last example of the year. Okay, so we're drawing dilations in the plane. So we're going to draw the image of the triangle with the given vertices under a dilation with a scale factor of -1/2, and it's going to be centered at the origin. Okay, so your k value they give you is -1/2. We know that the rule for the dilation of xy, okay, is kx, which is -1/2 x, and then -1/2 y. Okay, so kx, ky is -1/2 x, -1/2 y. So let's start with point P. So point P, -4, 4 to P prime is going to be multiplying -1/2 times -4, which is what? -4 times -1/2. Nope, you're right. Yeah, positive, right? Negative times negative would be a positive. Okay, so this would be 2. And then 4 times -1/2 is -2. So that's your P prime. Okay, and then the next one is Q. So you have -2, -2. So Q prime is just multiplying those by -1/2. What's -2 times -1/2? What's half of 2? 1, and then because it's negative times a negative, it'll be +1. And then this is the same coordinate, so that will be 1, 1. And then R is 4, 0. So what's half of 4? 2, so this would be -2, because you're multiplying by the negative. And then 0 times anything is just what? 0. Okay, so it says to draw the image of the triangle under the dilation. So we are going to draw both of these. Okay, so the first one, P is at -4, 4. Now, when you are drawing this, think to yourself how the other one is going to look. So we multiplied by -1/2. So is that going to get bigger or is that going to get smaller? Do you guys know why it's going to be smaller? It's the fraction, right? It has nothing to do with the negative. What does the negative actually do? It reflects it, yep. It's the reflection. And so here's your R. And then we're going to connect that with a straight edge. Image. Okay, so we definitely want to label these. This is going to be 2, -2. So that's my P prime. And then Q is 1, 1. then R is -2, 0. Right, so remember we talked about yesterday when we were doing the reflections, if you guys look, see how P and P prime are opposite of each other? Okay, same thing with R and R prime, and then Q and Q prime, because that's the reflection. Okay, and then your homework is going to be the 12.5, 12.7 worksheet.